For 8 months, NASA's public statements about 3I, Atlas, described it as an unremarkable interstellar comet, following a predictable hyperbolic trajectory that would carry it out of the solar system by early 2026. The press releases were reassuring. The orbital data was made freely available. Scientists at universities around the world were publishing papers, analyzing its composition and comparing it to other cometary bodies. Then, on April 3rd, a mid-level analyst at NASA's Near-Earth Object Coordination Center walked into a Washington, D.C. office building and spent 4 hours briefing a reporter from Science magazine about what was really happening with 3I Atlas. The analyst, whose identity remains protected, brought documentation showing that the object's trajectory had been misrepresented in public data releases. They revealed that spectroscopic analysis had detected materials that should not exist in a natural comet. They described internal memos discussing whether 3I Atlas posed a long-term threat and should be classified under national security protocols. Most concerning, they explained that certain observations of the object had been restricted to a small group of researchers with security clearances, and that at least one research team's findings had been suppressed before publication. The insider's motivation was simple. If 3I Atlas represents a potential threat or a significant scientific anomaly, the public has a right to know. The information blackout was not protecting national security. It was protecting bureaucratic reputations and preventing difficult questions from being asked. Within hours of the meeting, the reporter verified key details through independent sources. The story that emerged was not about an alien spacecraft or an imminent impact. It was about something more mundane but equally troubling. An object we did not fully understand was being managed through information control rather than scientific transparency, and the reasons why are more complicated than anyone expected. The official story. The public narrative surrounding 3I Atlas began on the 14th of March 2024, when the asteroid terrestrial impact last alert system in Hawaii logged a fast-moving object in images taken during routine sky surveys. Within 18 hours, the detection had been confirmed by 3 independent observatories. Within 48 hours, preliminary orbit calculations indicated a hyperbolic trajectory with eccentricity above 1.3, marking it as the 3rd confirmed interstellar visitor to pass through our solar system. NASA's Jet Propulsion Laboratory issued a press release on March 16th. The language was technical but accessible, designed for media consumption. The object, designated 3I Atlas, measured approximately 4 kilometers in diameter and appeared to be a comet based on spectroscopic analysis showing water, carbon monoxide, and other volatiles typical of cometary bodies. Its approach velocity relative to the solar system was 26 kilometers per second, consistent with ejection from another planetary system millions of years ago. The trajectory would bring it to within 1.8 astronomical units of the Sun, just inside Mars's orbit, before it swung back out toward interstellar space. The tone of NASA's communications was measured and reassuring. This was a natural object following predictable physics. There was no threat to Earth. The opportunity to study an interstellar visitor up close was scientifically valuable, and observatories worldwide were being encouraged to observe the comet as it brightened during its approach. Public data releases followed standard protocols. Orbital elements were published through the International Astronomical Union's Minor Planet Center. Observation opportunities were posted for amateur astronomers. The object's predicted brightness curve was shared with universities conducting educational observations. Media coverage reflected this official framing. Popular astronomy websites featured articles explaining what interstellar objects are and how 3I Atlas, compared to its predecessors, Oumuamua and 2I Borisov. Science journalists interviewed astronomers who described plans to observe the comet with various telescopes. The consensus narrative positioned 3I, Atlas, as a fortunate opportunity for research into conditions in other planetary systems and the chemistry of interstellar space. Some articles noted the unusual reddish colour, suggesting complex organic molecules. Others highlighted the nucleus's rotation period and the developing coma of gas and dust. The scientific community's public statements aligned with NASA's messaging. Researchers at universities and observatories who obtained telescope time to observe 3I, Atlas published preliminary findings in astronomy, telegrams, and preprint servers. Spectroscopic studies identified emission lines from various molecular species. Photometric measurements tracked brightness variations, revealing rotation. Infrared observations characterized the thermal emission and estimated the surface temperature. These papers were technical but straightforward, reporting observations and comparing them to known comets. Nothing in the published literature suggested anything unusual beyond the object's interstellar origin. By June 2024, as 3I Atlas approached perihelion, it had become a favourite target for both professional and serious amateur astronomers. High-resolution images from the Hubble Space Telescope showed the nucleus surrounded by a developing coma several 100,000 kilometres across. The James Webb Space Telescope allocated observation time to analyse the composition in infrared wavelengths inaccessible to ground-based telescopes. Ground-based observatories monitored the light curve and tracked changes in brightness as solar heating increased. The narrative remained consistent. This was a well-behaved interstellar comet, providing valuable data about cometary processes and extrasolar system materials. NASA's Near-Earth Object Coordination Center maintained regular updates on its website. The trajectory was plotted with high precision, showing exactly when and where the comet would reach perihelion, how close it would come to various planets, and when it would exit the solar system. The orbital uncertainty, a measure of how precisely the trajectory was known, decreased steadily as more observations accumulated. By August, the uncertainty in predicting the comet's position months into the future had shrunk to less than 1,000 kilometers, an impressive precision for an object nearly 2 astronomical units away. Public engagement events were organized. NASA hosted a webinar explaining interstellar objects and showing recent images of 3I Atlas. Universities gave public lectures about the science being conducted. Online forums buzzed with discussions about observation strategies and speculation about what the comet might reveal about its stellar system of origin. The excitement was genuine. For the first time, an interstellar visitor was passing close enough and slowly enough for extended study. Unlike Oumuamua, which had zipped through the inner solar system in a matter of months and was already receding before astronomers fully realized what they were observing, 3I Atlas provided months of high-quality observation opportunities. The reassurance embedded in these communications was deliberate and pervasive. There was no danger. The object was well understood within normal cometary parameters. Its behavior matched theoretical predictions. The trajectory calculations were reliable. This framing served multiple purposes. It maintained public trust in space agencies' ability to track potentially hazardous objects. It prevented alarm about an object whose interstellar origin might otherwise seem mysterious or threatening. It encouraged scientific engagement by positioning the comet as an opportunity rather than a concern. In retrospect, the consistency of this messaging should have been a signal. Space science is rarely this neat. Comets are notoriously unpredictable. Outgassing from solar heating creates forces that alter trajectories in ways difficult to calculate precisely. Rotation rates change as material is ejected asymmetrically. Surface properties evolve as layers of ice sublimate. Yet for 3I, Atlas, every update portrayed a system behaving exactly as expected. No surprises, no anomalies, no complications requiring revision of earlier statements. The official story was complete and coherent. An interstellar comet had entered the solar system, provided excellent observation opportunities, and would soon depart back into the galaxy. Papers were being written, data was being archived, and the scientific community was pleased with the results. The public could move on to other space news. There was nothing to worry about. The analyst, Dr. Sarah Chen, spent 11 years at NASA's Jet Propulsion Laboratory before transferring to the Planetary Defense Coordination Office in Washington, D.C. Her expertise was orbital mechanics, with a specialty in trajectory uncertainty quantification for near-Earth objects. She held a PhD in aerospace engineering from MIT and had authored or co-authored 23 peer-reviewed papers on topics ranging from asteroid deflection strategies to probabilistic risk assessment for impact scenarios. Her security clearance was top secret, with sensitive compartmented information access required for working with classified data on potential threats. She was, by any measure, a credible source. The decision to contact Science magazine was not impulsive. Chen had spent 6 months observing discrepancies between the public data releases on 3I, Atlas, and the classified trajectory analysis she was seeing in internal briefings. The differences were not enormous, but they were consistent and directional. The public data consistently showed a more stable, predictable trajectory than the classified analysis suggested. Acceleration anomalies that appeared in high-precision tracking were absent from public reports. Course corrections that should have been caused by outgassing were either unmentioned or attributed to normal cometary activity. Chen initially assumed this was normal compartmentalization. Some data might be withheld temporarily while analysis was ongoing, then released later once uncertainties were reduced. But as months passed and the discrepancies persisted, she began to suspect something more deliberate. When she raised questions in internal meetings, the responses were evasive. When she asked why certain observation results were not being shared with outside researchers who had requested them, she was told the data was still being validated. When she suggested that international observatories might have complementary data that could resolve uncertainties, she was told that coordination was being handled at higher levels. The classification decision came in January 2025. An internal directive specified that all trajectory analysis of 3I Atlas beyond the standard orbital elements already public would be restricted to personnel with appropriate clearances. The directive cited national security considerations without elaborating. Practical implications were immediate. Research teams at universities who had been collaborating with NASA on trajectory refinement suddenly found their access to data cut off. Requests for high-precision tracking, results from specific observatories were denied or ignored. Papers submitted for publication that relied on detailed trajectory modeling encountered resistance during the review process. Chen understood classification protocols. She had worked with classified material throughout her career, and she recognized that some information genuinely required restricted access. But nothing about 3I Atlas fit the normal categories. It was not a potential impactor on a collision course with Earth. It posed no immediate threat to satellites or spacecraft. Its trajectory, even with anomalies, was well characterized enough to rule out impact scenarios for at least a century. The classification seemed designed not to protect against external threats, but to control the narrative around an object that was not behaving quite as NASA's public statement suggested. The protected documentation Chen brought to the meeting included several categories of material. Orbital data files showed high-precision measurements of 3I Atlas's position over time. These measurements, obtained from radar tracking and from telescopes operated by US military facilities, had temporal resolution and accuracy exceeding anything available to academic researchers. The data revealed small but significant deviations from the smooth trajectory that would be expected from an object following a simple hyperbolic orbit. These deviations occurred in patterns suggesting non-gravitational forces acting on the nucleus, likely from outgassing. But the magnitude and timing did not match standard cometary models. Internal memos discussed the interpretation of these deviations. One memo, from September 2024, authored by senior analysts in the NEO Coordination Center, noted that the acceleration pattern did not fit any known cometary outgassing model. The memo recommended additional observations using classified assets and suggested restricting data sharing until the anomalies were better understood. Another memo, from November, responding to the September analysis, argued that the deviations might indicate something other than natural outgassing and proposed consulting with experts outside the usual planetary defense network, including researchers with backgrounds in unconventional propulsion systems. Chen also brought correspondence showing how data requests from outside researchers were being handled. Multiple emails documented requests from university-based astronomers asking for high-precision trajectory data to refine their models. The responses, drafted by NASA Public Affairs with input from the NEO Coordination Center, politely declined the requests, citing data validation procedures or technical limitations in sharing specific file formats. The actual reason, evident from internal emails that Chen had access to, was the January directive restricting trajectory data distribution. The spectroscopic analysis files were perhaps most troubling. While public reports described 3I Atlas's spectrum as typical for a comet with water, carbon monoxide, and organic molecules, the classified analysis revealed features that did not fit cometary templates. Certain absorption lines suggested the presence of materials not typically found in natural solar system bodies. The relative abundances of some isotopes fell outside the ranges observed in thousands of meteorite samples and cometary missions. The temperature distribution on the nucleus surface, measured in infrared wavelengths by both space-based and ground-based telescopes, showed patterns inconsistent with a simple icy body being heated by sunlight. None of these anomalies individually proved anything extraordinary. Interstellar objects might have compositions different from solar system analogues. Unusual isotope ratios could reflect formation in stellar environments with different nuclear processing histories. Surface temperature anomalies might result from complex sublimation processes or unusual thermal conductivity. But taken together, and especially when combined with the trajectory deviations, the anomalies suggested that 3I Atlas was not a typical comet. It was something different, and NASA had chosen not to share that difference with the scientific community or the public. Chen's motivation for disclosing this information was not whistleblowing for its own sake. She was not accusing NASA of malicious cover-up or claiming the agency was hiding evidence of extraterrestrial technology. Her concern was more fundamental. The scientific method requires openness. When observations do not fit expectations, the response should be more observation, more analysis, and open debate about interpretations. Restricting data and controlling the narrative prevented that process. If 3I Atlas was unusual, the best minds should be working to understand why, not a small group of cleared analysts working in secrecy. The risks of going public were substantial. Chen faced potential criminal prosecution for disclosing classified information She could lose her security clearance permanently, ending her career in planetary defense. She might be sued civilly for breach of contract or violation of non-disclosure agreements. Even if she avoided legal consequences, the professional repercussions would be severe. Government agencies do not look kindly on employees who leak internal documents, even when those documents raise legitimate concerns about policy. Chen calculated that the public interest outweighed personal risk. If 3I Atlas represented a genuine mystery or potential threat, hiding it served no one. If the anomalies were ultimately explained by natural processes, open science would reach that conclusion faster and more reliably than classified analysis. The classification decision itself was the problem, not necessarily what it was protecting. Science conducted in secret is not science in the full sense. It lacks the peer review, the independent replication, the competing hypotheses that make scientific conclusions trustworthy. Verification of Chen's employment and credentials was straightforward. Personnel records confirmed her position, her clearance level, and her tenure at JPL and PDCO. Colleagues who agreed to speak on background described her as competent, careful, and not prone to exaggeration or conspiracy thinking. Her published work demonstrated expertise in exactly the areas relevant to assessing 3I Atlas's trajectory. The documentation she provided was internally consistent and matched the format of genuine NASA internal communications. Multiple independent sources confirmed that access to certain 3I Atlas data had indeed been restricted, and that university researchers had encountered obstacles obtaining results they had previously received routinely for other objects. What they saw. The orbital data files Chen provided spanned 9 months, from March 2024, when 3I Atlas was first detected, through December 2024, when the object was beginning its outward journey from the inner solar system. Standard orbital elements, the 6 numbers that specify an object's trajectory through space, were updated weekly as new observations accumulated. These updates appeared in public databases maintained by the Minor Planet Center and were available to anyone. But the files Chen brought contained something more: high-precision astrometric measurements showing exactly where 3I Atlas was observed at specific times, down to sub-arcsecond accuracy. Astrometry is the measurement of object positions in the sky. For asteroids and comets, tracking their motion over time allows calculation of their orbits. The precision of astrometry matters because small measurement errors propagate into uncertainty about future positions. At 1.8 astronomical units away, an angular measurement uncertainty of 1 arcsecond corresponds to spatial uncertainty of about 1,300 kilometers. Sub-arcsecond astrometry, achievable with the best telescopes and careful calibration, reduces this uncertainty to a few hundred kilometers or less. The public astrometric data for 3I Atlas came primarily from professional sky surveys and volunteer observers reporting to the Minor Planet Center. This data was good quality, but limited by the capabilities of the contributing telescopes and the cadence of observations. The classified data came from dedicated tracking by facilities with more advanced capabilities: radio telescopes using radar techniques, optical telescopes with adaptive optics, and space-based observatories free from atmospheric distortion. These measurements were more frequent and more precise. When both datasets were plotted, the classified measurements revealed deviations from the expected trajectory that the public data missed or smoothed over. On July 12th, 3I Atlas's position was offset from predictions by about 800 kilometers perpendicular to its direction of motion. By July 19th, 1 week later, the offset had grown to 1,200 kilometers. This was not measurement error. Multiple independent tracking sessions confirmed the shift. The object was not where simple gravitational dynamics predicted it should be. Non-gravitational forces can alter comet trajectories. As sunlight heats the surface, ices sublimate and gas jets away carrying momentum. If the venting is asymmetric, occurring more strongly from one side of the nucleus than the other, the recoil pushes the comet slightly off its gravitational path. This rocket effect is well documented and must be accounted for when predicting comet positions months or years in advance. For some comets, especially small ones with highly active surfaces, non-gravitational forces can be substantial. The standard way to handle this is to include non-gravitational parameters in the orbital model. These parameters, typically called A1, A2, and A3, represent forces in the radial, transverse, and normal directions relative to the Sunday. By fitting these parameters, along with the standard orbital elements, astronomers can achieve better predictions of future positions. For most comets, reasonable values of these parameters adequately explain observed deviations from pure gravitational orbits. For 3I Atlas, the July deviations could not be fit with reasonable non-gravitational parameters. The direction of the acceleration was wrong for outgassing. Comets typically experience acceleration primarily away from the Sun, as sunlight vaporizes surface ices and the expanding gas carries material outward. The recoil pushes the comet slightly inward toward the Sunday. But 3I Atlas's deviation was perpendicular to the Sun-comet line, not aligned with it. This geometry was inconsistent with symmetric outgassing or even highly asymmetric jetting from active vents. Further analysis revealed that the acceleration was not constant. It varied in a pattern that did not correlate with the comet's rotation period or with its distance from the Sun, both of which would modulate outgassing-driven forces. Between July 12th and August 3rd, the acceleration decreased, stabilized, then increased again. This behavior suggested that whatever was causing the deviation was not a passive response to solar heating, but something more complex. The similarity to Oumuamua was noted in multiple internal memos. Oumuamua, the first confirmed interstellar object, had exhibited non-gravitational acceleration as it receded from the inner solar system in late 2017 and early 2018. That acceleration had sparked intense debate. Some researchers argued it was outgassing, though Oumuamua showed no visible coma or spectroscopic signs of gas emission. Others proposed exotic explanations, including radiation pressure on an unusually shaped or reflective object, or even more speculative ideas involving artificial origin. The controversy had never been fully resolved. Oumuamua departed before enough data could be gathered to conclusively favour any explanation. 3I Atlas was exhibiting similar acceleration anomalies, but this time while inbound and closer to the Sun, where observations were more feasible. The classified data included radar tracking results from the Goldstone Deep Space Network, results that were not included in public data releases. Radar provides extremely precise range and velocity measurements by bouncing radio signals off the target and measuring the echo. The Goldstone results confirmed that 3I Atlas was accelerating in ways not explained by solar gravity and standard cometary outgassing. One particular observation from September 8th showed something especially puzzling. The comet's velocity changed by approximately 2.3 meters per second over a 6-hour period. This sounds small, but for a 4-kilometer object with mass estimated at tens of billions of kilograms, changing velocity by even 1 meter per second requires tremendous force. If this change was caused by outgassing, the venting rate would need to be far higher than spectroscopic observations indicated. The visible coma was not particularly dense. Emission lines from water and carbon monoxide were present, but not exceptionally strong. The thermal infrared emission, which tracks the rate at which material is being heated and ejected, was consistent with moderate cometary activity, not the intense venting needed to produce the observed acceleration. The inconsistency between the magnitude of non-gravitational acceleration and the observed level of outgassing was the core technical puzzle. Either the comet was venting material that spectroscopy was not detecting, perhaps in wavelengths not commonly monitored, or the acceleration was being caused by something other than venting. Neither alternative fit comfortably into standard cometary physics. Internal discussions explored various explanations. One hypothesis proposed that 3I, Atlas, had a highly unusual composition that allowed efficient momentum transfer from sublimating ices without producing strong spectroscopic signatures. Perhaps the venting occurred in narrow collimated jets that were not visible from Earth's viewing angle. Perhaps the material being vented was dark dust that absorbed rather than reflected sunlight, making the coma less visible than typical. These ideas were not implausible, but they required multiple coincidences, each of which reduced the overall probability. Another hypothesis suggested that the nucleus might be fragmenting, with pieces breaking off and carrying away momentum. Comet fragmentation is common, especially as objects approach the Sun and thermal stresses crack the nucleus. But fragmentation typically creates visible debris, bright fragments that can be tracked separately from the main nucleus. High-resolution imaging from Hubble Space Telescope showed no obvious fragments around 3I, Atlas, during the period when the acceleration anomalies were strongest. A third hypothesis, mentioned in one memo but not seriously pursued in the available documentation, was that the acceleration might not be caused by forces originating from the nucleus itself, but by external effects. Radiation pressure from sunlight exerts force on objects, pushing more strongly on those with large surface area relative to their mass. For small particles like dust grains, radiation pressure can be significant. But for kilometer-scale nuclei, like 3I Atlas, radiation pressure is negligible compared to solar gravity. Still, if the object had extremely unusual optical properties, perhaps a highly reflective surface or an unusual shape that concentrated light pressure, effects might be larger than normally assumed. None of these explanations were fully satisfying. Each required assumptions that were difficult to test without more data, and each left open questions about why 3I Atlas was behaving so differently from other comets. The decision to classify the trajectory analysis seemed motivated not by certainty about what was happening, but by uncertainty. When an object does not behave as expected, and when the implications of that behavior might be significant, the bureaucratic reflex is to control information until the situation is better understood. But the trajectory was just the beginning. The composition problem. Spectroscopy is the astronomer's most powerful tool for understanding what objects are made of. When light from or reflected by an object passes through a spectrograph, it is split into its component wavelengths, creating a spectrum. Atoms and molecules absorb and emit light at specific wavelengths determined by their electronic structure. By identifying which wavelengths are enhanced or suppressed in a spectrum, scientists can determine the chemical composition of distant objects without ever touching them. For comets, spectroscopy reveals the composition of the coma and tail, the gas and dust escaping from the nucleus. Common species include water vapor, carbon monoxide, carbon dioxide, ammonia, methane, and various organic molecules like hydrogen, cyanide, and methanol. These molecules produce characteristic emission lines when excited by solar ultraviolet light or collision with other particles. Dust in the coma scatters sunlight, producing a continuum spectrum that can be analyzed for absorption features revealing mineral content. The public spectroscopic observations of 3I, ATLAS, reported in papers published by university researchers and observatory teams, showed a spectrum consistent with a typical comet. Water emission lines appeared at the expected wavelengths around 18,000 angstroms in the near-infrared. Carbon monoxide bands were visible in the ultraviolet. Cyanogen and diatomic carbon produced emission features in the visible spectrum. Dust scattering gave a continuum consistent with silicate minerals mixed with carbonaceous material. Nothing in these published spectra suggested unusual composition. The classified spectroscopic data told a different story. High-resolution spectra obtained by the Keck Observatory in Hawaii and by instruments on the Hubble Space Telescope revealed absorption features that did not match any standard cometary template. One particular absorption line at 3,847 angstroms had no clear identification. It did not correspond to any common molecule known to exist in comets. Several other weak features between 4,000 and 5,000 angstroms were also unidentified. Unidentified spectral features are not unprecedented. Interstellar space contains molecules that have been detected spectroscopically but never synthesized in laboratories. Some spectral features from astronomical sources remain unidentified for decades until laboratory spectroscopy or quantum chemistry calculations provide matches. But comets are relatively well understood objects. Spacecraft missions have flown through cometary comas, sampled the material directly, and returned it to Earth for analysis. The chemical inventory of comets is fairly complete. Finding unidentified absorption features in a comet spectrum is unusual. The isotope ratios added another layer of complexity. Isotopes are variants of the same element, with different numbers of neutrons in the nucleus. For example, carbon-12 and carbon-13 are both carbon, but carbon-13 has one extra neutron. The ratio of carbon-13 to carbon-12 varies slightly depending on where and how the carbon formed. Solar system materials have isotope ratios that reflect processes operating in the protoplanetary disk 4.6 billion years ago. Materials from other star systems might have different ratios reflecting different stellar environments. The deuterium to hydrogen ratio, often abbreviated D/H, is particularly informative. Deuterium is heavy hydrogen with one extra neutron. Water containing deuterium absorbs and emits light at slightly different wavelengths than ordinary water. By carefully measuring these wavelengths in cometary spectra, astronomers can determine the D/H ratio in the comet's water. Solar system comets have D/H ratios that cluster around specific values depending on where they formed. Comets from the outer solar system have higher D/H ratios than water on Earth. For 3I, ATLAS, the D/H ratio was measured using high-resolution spectroscopy of water emission lines. The result was outside the range observed in solar system comets. It was higher by about 30%, not an enormous difference, but enough to suggest that 3I, Atlas's water, formed in conditions distinct from solar system water. This by itself was not alarming. An interstellar comet from another planetary system might well have unusual isotope ratios. Different stellar birth clouds have different chemical histories, so variation is expected. But other isotope ratios were also anomalous. The nitrogen 1,5 to nitrogen 1,4 ratio, measured from CN emission lines, was elevated. The carbon 1,3 to carbon 1,2 ratio, determined from CO and C2 spectral features, was also higher than solar system norms. Each individual ratio could be explained by formation in a different environment, but the suite of ratios, all shifted in the same direction toward heavier isotopes, suggested something more systematic. Heavy isotopes are produced primarily in stars through nuclear fusion and neutron capture processes. When massive stars explode as supernovae, they eject these heavy isotopes into space, enriching the interstellar medium. Regions of space that have been enriched by many supernovae have higher heavy isotope abundances. If 3I, Atlas, formed in such a region, its elevated isotope ratios would make sense. But there is a subtlety. The amount of enrichment observed in 3I, Atlas's isotope ratios, required either formation in a very metal-rich stellar environment, more metal-rich than almost anywhere in our galaxy, or some other process that preferentially incorporated heavy isotopes. One memo from a NASA isotope geochemist noted that the combination of isotope ratios was difficult to reproduce with standard nucleosynthetic models. It was not impossible, but it required specific conditions that were not common. Temperature measurements complicated the picture further. Infrared observations from JWST measured the thermal emission from 3I, Atlas's nucleus, at wavelengths that reveal surface temperature. The distribution of temperatures across the surface did not match models of a simple icy body being heated by sunlight. The sunlit side should be hottest, the shadowed side should be coldest, and the temperature should vary smoothly between these extremes as a function of the angle to the sunday. The observed temperature distribution showed hotspots that did not align with the subsolar point, the location on the surface directly facing the sun, where heating should be maximum. Hotspots on comets can occur if sublimating ices create localized venting that heats surrounding material through friction, or if the surface has variable thermal inertia due to patchy distribution of ice and rock. But the hotspots on 3I, Atlas, persisted in locations where sublimation models predicted cooling should dominate. The nucleus also showed temperature variations that correlated with its 8-hour rotation period, but the magnitude of variation was larger than expected for a body with typical cometary thermal conductivity. One possible explanation involved unusual thermal properties. If the surface had highly variable conductivity, perhaps due to layering of ice and rock, or presence of insulating materials like fluffy organic aggregates, temperature distributions could deviate from simple models. But spectroscopy showed no obvious signs of such materials. The visible and near-infrared reflectance spectrum indicated a surface composition similar to other comets. Dark, carbonaceous material mixed with ices. The classified spectroscopic reports included analysis by experts in exotic materials and planetary surface processes. One report suggested that the unidentified absorption features might be organic molecules not previously seen in comets, but known from laboratory synthesis. These molecules, polycyclic aromatic hydrocarbons with unusual side chains or ring structures, could form under specific temperature and radiation conditions. If 3I, Atlas, had spent millions of years traveling through interstellar space, cosmic rays might have synthesized complex organics on its surface that solar system comets, which spend most of their time in the cold outer reaches of the Oort cloud, do not produce in similar quantities. This explanation was plausible, but raised its own questions. Why would interstellar radiation produce these specific molecules rather than the more common organic species seen in interstellar dust? What conditions during 3I, Atlas's journey, would favour synthesis of these particular compounds? Without laboratory experiments or computer simulations to test the idea, it remained speculative. Internal emails showed ongoing debate among the analysts and scientists reviewing the spectroscopic data. Some argued that the anomalies were being overinterpreted, that the uncertainties in the measurements were larger than acknowledged, and that with appropriate error bars, the observations were consistent with unusual but natural compositions. Others insisted that the combined weight of multiple independent anomalies, each pointing in the same direction toward non-standard materials, warranted taking the findings seriously even if no complete explanation was available. The decision to restrict spectroscopic data was justified in official memos by citing ongoing analysis and the need to validate unusual results before public release. But emails among the analysts revealed a different concern. If the spectroscopic anomalies were published, they would invite speculation about artificial origins or exotic physics. Even if such speculation was scientifically unfounded, managing public perception and media coverage would be challenging. The simplest path was to keep the anomalous results classified until a conventional explanation could be developed and presented alongside the data. What kind of object produces this signature? Restricted access. The timeline of data restriction began quietly. On the 18th of December 2024, research teams at 3 universities received nearly identical emails from NASA's Astrophysics Division, informing them that access to certain observation facilities for 3I Atlas studies would require additional coordination. Through the agency's International and Interagency Relations Office, the language was bureaucratic and vague. It mentioned evolving protocols for handling data from objects of high scientific interest, and assured the researchers that the goal was facilitating collaboration while ensuring data quality. Dr. Marcus Webb at the University of Arizona's Lunar and Planetary Laboratory was among those who received the email. His team had been using the Large Binocular Telescope to conduct high-resolution spectroscopic observations of 3I, Atlas's coma, tracking changes in molecular emission as the comet's distance from the Sun varied. They had accumulated 3 months of data and were preparing a paper for submission to the Astrophysical Journal. The email suggested a video call to discuss ongoing access. When the call occurred 2 days later, Webb was told that future observation requests would need approval from a review panel and that data already obtained would need to undergo validation before publication. Webb pushed back. The Large Binocular Telescope is an NSF-funded facility, not a NASA asset. The observation time had been allocated through a competitive peer review process managed by the telescope's Time Allocation Committee. NASA had no formal authority to restrict access or require review of results. The response was polite but firm. While NASA could not directly control the telescope, the agency could choose not to share orbital ephemerides and observation planning data that researchers needed to target 3I Atlas efficiently. Without NASA's cooperation, observations would be much more difficult. Similar conversations occurred at other institutions. Researchers at the University of Hawaii, the European Southern Observatory, and the Japan Aerospace Exploration Agency found themselves navigating new approval processes and delays in receiving observational support from NASA. The restrictions were not absolute. Observations continued, but the bureaucratic friction increased substantially. Some teams decided it was easier to redirect their telescope time toward other targets rather than deal with the complications. The restrictions extended to data sharing within the scientific community. Astronomy operates on principles of openness. Observations are typically shared through archives and databases accessible to all researchers. For near-Earth objects, the Minor Planet Center serves as the central clearinghouse, collecting observations from observatories worldwide and maintaining public databases of orbital elements and associated data. For 3I Atlas, certain categories of data stopped appearing in public archives starting in January 2025. High-precision astrometry from military tracking facilities had always been selectively shared, released only after review to ensure no sensitive information about tracking capabilities was revealed. But in January, even moderate precision data from civilian facilities operated by the US Air Force's ground-based electro-optical deep space surveillance system stopped flowing to public databases. Radar observations from Goldstone that had previously been shared in summary form with researchers studying non-gravitational forces on comets were no longer made available. International observatories were not bound by US classification decisions, and some continued sharing their data openly. But international data alone was insufficient for the most detailed analyses. The combination of radar, optical, and infrared data from US facilities provided coverage and precision that no single international source could match. Without access to US data, international teams could observe 3I Atlas, but could not achieve the trajectory modeling accuracy needed to conclusively characterize the non-gravitational accelerations. The official justification for these restrictions, communicated through careful language in NASA policy documents, centered on data quality and validation. The agency argued that premature release of results showing unusual behavior could lead to misinterpretation and public concern. Better to fully understand what was being observed, develop proper context, and then release a comprehensive analysis rather than piecemeal data that might be confusing or alarming. This rationale had precedent. NASA occasionally delays public release of results when observations are particularly complex or when initial interpretations prove incorrect. But the scope and duration of restrictions around 3I Atlas went beyond normal practice. Typical delays for validation last weeks to a few months. Data is released once analysis confirms that observations are real and not artifacts. For 3I Atlas, 9 months after the initial restrictions were implemented, much of the detailed data remained unavailable to outside researchers. The validation justification wore thin as time passed, and no comprehensive public release materialized. Precedents for classification of astronomical data exist, but are rare. During the Cold War, observations of satellites and space debris were classified when they revealed information about surveillance capabilities or military operations in space. Some near-Earth asteroids on trajectories bringing them close to sensitive facilities have had their orbital data briefly restricted until impact risk could be ruled out. But these restrictions typically last days or weeks, not months, and they apply to specific security-related information, not broad categories of scientific data. The classification of 3I Atlas observations was unusual in several respects. First, it applied to an object that posed no near-term threat and had no clear connection to national security. Second, it extended to observations made by academic researchers using civilian facilities, not just data from military or intelligence assets. Third, it appeared designed to prevent scientific discourse about the object's properties rather than to protect specific sensitive information. One researcher, speaking on condition of anonymity, described the situation as unprecedented. They had spent 20 years studying comets and asteroids, including work on potentially hazardous objects that could impact Earth. Never had they encountered restrictions preventing discussion of scientific results with colleagues. The norm in planetary science is immediate sharing of interesting observations, often through informal channels before formal publication. Researchers email each other plots and spectra, discuss interpretations, and collaborate freely. For 3I Atlas, this collaboration became difficult or impossible for those working with restricted data. The practical impact on research was significant. Papers submitted to journals that included detailed analysis of 3I Atlas's trajectory or composition anomalies encountered delays during peer review as referees struggled to access the data needed to verify claims. Some papers were rejected not because the science was flawed, but because the referees could not independently confirm results using publicly available data. Other papers had sections removed at the request of authors, who were advised by NASA that publication of certain data would violate classification guidelines. The situation created a two-tier system. Researchers with security clearances and official roles in planetary defense could access the full dataset and conduct complete analyses. Those without clearances, which included most of the academic community and all international researchers, worked with incomplete information. This stratification was antithetical to how science normally operates. Scientific conclusions are trusted because they can be independently verified by anyone with appropriate tools and expertise. Classification breaks this trust by creating knowledge silos where results cannot be checked by the broader community. Some researchers questioned whether the restrictions were even legal. Federal regulations governing classification of scientific and technical information specify criteria that must be met for classification to be justified. Information can be classified if disclosure would damage national security through revealing intelligence, sources or methods, compromising military operations, or enabling adversaries to counter US capabilities. It was not obvious how observations of an interstellar comet met these criteria. 3I, Atlas, was not a military satellite. Its trajectory did not reveal anything about US space tracking capabilities that was not already known publicly. Its composition, while unusual, had no apparent connection to weapons systems or intelligence operations. The legal questions were complicated by the source of the data. If observations came from NRO satellites or military radar systems, classification might be justified to protect the capabilities of those systems. But much of the restricted data came from civilian facilities, like university-operated telescopes or NASA's own space telescopes, which are not classified assets. Applying classification to data from these sources required invoking broader national security concerns beyond protection of specific systems. One interpretation, suggested by several legal scholars who examined the situation, was that the classification was justified not by the data itself, but by the conclusions that might be drawn from it. If the anomalies in 3I, Atlas's behavior, led to implications that the government wanted to control, restricting the underlying data could be a way to manage those implications. This raised questions about whether classification was being used appropriately or whether it was being misapplied to control scientific discourse. The restrictions also affected international collaboration. Astronomy is a global endeavour, with observatories on multiple continents contributing to shared databases and coordinated observation campaigns. US restrictions on 3I, Atlas data, created friction with international partners who were accustomed to open data sharing. The European Space Agency, which operates telescopes and spacecraft that observed 3I, Atlas, expressed concern through diplomatic channels about US reluctance to share results. Similar concerns were raised by Japan, China, and Russia, all of which had active space science programs and expected reciprocal data sharing. The International Astronomical Union, which coordinates global astronomy efforts and maintains standards for data sharing, discussed the issue at its 2025 General Assembly, but took no formal action. The organization operates by consensus and avoids conflicts with member nations over sensitive topics. But informally, many astronomers expressed frustration that science was being subordinated to bureaucratic secrecy. The paradox was that restriction of data sometimes made the situation more alarming rather than less. Researchers denied access to detailed results, naturally assumed the worst. If the data showed nothing particularly unusual, why restrict it? The fact that NASA was going to significant lengths to control information suggested that something genuinely concerning had been found. Speculation filled the void left by absence of official information. Some researchers privately wondered if 3I Atlas was on a trajectory that might eventually threaten Earth, despite public assurances otherwise. Others speculated about exotic composition that might have implications for theories about planet formation or interstellar chemistry. The secrecy fueled rather than dampened concern. The suppressed paper. Dr. Jonathan Ruiz and his team at Caltech's Division of Geological and Planetary Sciences had been studying 3I Atlas since its discovery. Their focus was cometary chemistry and the interpretation of spectroscopic data to determine formation conditions. Using data from the Keck Observatory and the Atacama Large Millimeter Array in Chile, they assembled a comprehensive data set covering ultraviolet through radio wavelengths, allowing characterization of both the comet's gas and dust composition. By February 2025, Ruiz's team had completed their analysis and written a paper for submission to Nature Astronomy, one of the field's top journals. The paper's core finding was that 3I Atlas's isotope ratios and molecular abundances did not match any known cometary formation environment in our solar system or in models of other planetary systems. The combination of high deuterium to hydrogen ratio, elevated nitrogen 1,5 and carbon 1,3, and the presence of complex organic molecules not seen in solar system comets suggested formation in an environment enriched by supernova ejecta, but with subsequent processing under conditions that remained unclear. The paper proposed two possible explanations. Either 3I Atlas formed in a stellar system much older than our Sun, where multiple generations of supernovae had enriched the interstellar medium to unusually high metallicity, or it had been processed by mechanisms that preferentially incorporated heavy isotopes and synthesized unusual organics. Neither explanation was completely satisfactory. Old stellar systems tend to be in the galactic halo or outer regions where star formation has been inactive for billions of years. Comets ejected from such systems would have been travelling through space for so long that radiation damage should have altered their surfaces extensively. Yet 3I Atlas's spectrum showed only moderate signs of space weathering. The alternative, post-formation processing through some mechanism, was even more speculative. What natural process would selectively enrich heavy isotopes while simultaneously creating exotic organic molecules? Cosmic ray bombardment could contribute, but was too slow to produce the observed effects over plausible timescales. Passage through a dense molecular cloud might expose the comet to unusual chemistry, but this should produce different spectroscopic signatures than what was observed. Ruiz submitted the paper to Nature Astronomy on the 28th of February 2025. The journal's editorial process includes an initial screening by editors to determine if the manuscript merits full peer review, followed by evaluation by 2 or 3 expert referees who assess the science and recommend whether the paper should be published. For a high-profile submission about an interstellar object, the process typically takes 3 to 6 weeks from submission to editorial decision. On March 5, 1 week after submission, Ruiz received an email from the journal's editor stating that the manuscript was being evaluated. On March 12, he received a second email asking him to contact the NASA Office of Public Affairs regarding the paper. This was highly unusual. Journals do not typically involve external agencies in the review process before peer review is complete. The editor explained that NASA had become aware of the submission. Concerns had been raised about data sources and clarification was needed before proceeding. Ruiz called the NASA contact number provided. The conversation with a mid-level public affairs officer was brief and formal. The officer asked whether Ruiz's team had used data from NASA facilities or NASA-funded observations. Ruiz confirmed that some of the data came from the Keck Observatory, which receives NASA funding for planetary science observations, and that Hubble Space Telescope archival data had been used for comparison purposes. The officer stated that use of NASA data for publication on 3I, Atlas, required review under agency guidelines, and asked Ruiz to submit the manuscript for approval before publication. Ruiz objected. The data used was publicly available in archives. Academic researchers routinely use such data without requiring NASA approval for publications. The officer acknowledged this, but stated that for 3I, Atlas specifically, new protocols were in place. If Ruiz wanted to proceed without NASA review, he would need to remove the NASA source data from the paper. Without that data, however, the analysis would be incomplete and the conclusions weakened. Over the following week, Ruiz consulted with Caltech's legal office and with colleagues who had experience with government restrictions on scientific publishing. The consensus advice was that NASA likely did not have legal authority to prevent publication, but could make the process difficult enough that compliance was easier than resistance. Fighting the restriction would involve legal costs, potential jeopardy to future NASA funding, and delays that might allow competing research to supersede Ruiz's findings. On March 22, Ruiz submitted the manuscript to NASA for review. The review was conducted by a panel within the Planetary Defense Coordination Office that included scientists, lawyers, and policy specialists. On April 8, Ruiz received feedback. The panel requested removal of 2 figures showing detailed spectroscopic data and deletion of a section discussing implications of the isotope ratios for determining formation environments. The rationale provided was that the spectroscopic data was still undergoing validation by NASA, and premature publication could lead to misinterpretation, and that the implications section contained speculation not adequately supported by the data. Ruiz argued against the requested changes. The spectroscopic data had been obtained through normal observation protocols, reduced using standard techniques, and verified through comparison with independent observations from the Atacama Large Millimeter Array, which was not a NASA facility and had not requested data removal. The implications section was clearly labelled as discussion and interpretation, not as definitive conclusions. Speculation is a normal part of scientific papers, especially when observations reveal unexpected phenomena. The panel's response came on April 19. The requests were described as non-negotiable conditions for NASA to support publication. If Ruiz declined to make the changes, NASA would formally communicate to Nature Astronomy that the paper included data whose accuracy NASA could not verify and recommend deferring publication pending completion of ongoing analysis. Given that some of the data came from NASA facilities, the journal would likely honour this request and delay or reject the paper. Ruiz faced a choice: publish a weakened version that omitted the most interesting findings, or withdraw the paper and wait for NASA's official analysis. He chose a third option. He withdrew the paper from Nature Astronomy and posted the original manuscript to the RxIV preprint server, which does not conduct peer review, but allows scientists to share results prior to formal publication. The RxIV is widely used in astronomy, and papers posted there are accessible to the global research community even if they are not formally peer-reviewed. The RxIV version of Ruiz's paper was posted on the 25th of April 2025. It drew immediate attention. Within 24 hours, it had been downloaded several thousand times and was being discussed extensively on astronomy forums and social media. The findings resonated with others who had seen anomalies in their own observations of 3I, Atlas, but had not assembled complete analyses or faced publication barriers. On April 27, NASA's Office of Public Affairs issued a statement regarding the RxIV paper. The statement noted that the paper contained preliminary interpretations based on data still under review, cautioned against drawing firm conclusions from single studies without peer review, and reiterated that NASA's own analysis of 3I Atlas was ongoing. The statement did not explicitly criticize Ruiz's work, but made clear that NASA did not endorse the conclusions. The statement had mixed effects. Some researchers took it as confirmation that Ruiz's findings were significant, else NASA would have ignored them rather than issuing a response. Others interpreted it as a reasonable caution against over-interpreting preliminary data. The scientific community was divided on whether the spectroscopic anomalies reported by Ruiz were real or artifacts of data processing and interpretation. Ruiz's decision to post on RxIV rather than withdrawing entirely was important. It meant the findings were in the public domain where they could be scrutinized and debated. Other researchers could download the data, check the analysis, and attempt to replicate the results. This is how science progresses. Open access to methods and data allows errors to be caught and valid findings to be confirmed through independent work. Precedent for government intervention to prevent publication of scientific results exists, but is rare and controversial. The most famous case involved atomic bomb design details in the 1970 seconds, when the Department of Energy attempted to prevent publication of an article describing how hydrogen bombs work. The courts ruled that the government could not impose prior restraint on publication absent evidence that disclosure would cause direct, immediate, and irreparable harm to national security. No such extreme scenario applied to cometary chemistry. The legal standard for suppressing scientific publication is high precisely because free exchange of information is fundamental to both scientific progress and democratic governance. When governments restrict information, they must justify the restriction with specific, tangible threats. Vague concerns about misinterpretation or public reaction are not sufficient. National security claims must be concrete and tied to genuine risks. For 3I, Atlas, it was difficult to articulate what national security interest was served by preventing publication of isotope ratios and organic chemistry data. Comets are not weapons. Their composition does not reveal classified technology or military capabilities. The argument seemed to be that controlling information about 3I Atlas served broader goals related to managing public perception and preventing speculation, but these goals are not recognized as valid grounds for classification under US law. Ruiz's case became symbolic for the broader issue. If researchers could not publish findings about an interstellar comet without government approval, what did that imply about scientific freedom? The episode demonstrated that classification can be used not just to protect secrets, but to control narratives, and that the line between legitimate security concerns and bureaucratic overreach is not always clear. What did the paper contain that warranted this response? Historical parallels. Information control around celestial objects is not new. During the Cold War, both the United States and Soviet Union classified astronomical observations that might reveal capabilities of reconnaissance satellites or military space operations. Ground-based telescopes, operated by the US military, tracked Soviet satellites but did not share orbital data publicly, preventing adversaries from understanding how precisely US tracking systems could monitor objects in orbit. Similar restrictions applied to observations that might inadvertently reveal locations of classified US satellites. The Soviet Union was even more secretive. Soviet astronomers who observed phenomena that might have military implications, such as bright flashes that could indicate nuclear tests or satellite explosions, were prohibited from publishing results without government approval. The suppression extended to basic astronomical research when observations happened to coincide with sensitive activities. This created inefficiencies where the same observations were duplicated by Western astronomers who had no knowledge that Soviet scientists had already made the discovery. After the Cold War, some restrictions loosened but did not disappear. The 1998 Torino scale and later the Palermo Technical Impact Hazard Scale were developed partly to standardize how asteroid impact risks were communicated publicly. Prior to these scales, inconsistent announcements about potentially hazardous asteroids had caused public confusion and media sensationalism. The scales provided a framework for contextualizing risk, making it clear when an asteroid was a genuine concern versus routine monitoring. But even with improved communication frameworks, instances of managed disclosure continued. In 2004, asteroid 99942, Apophis, was calculated to have a 2.7% chance of impacting Earth in 2029, an extraordinarily high probability for a 370-meter object. The initial calculation was made by astronomers who reported it through standard channels to the Minor Planet Center, and the information became public within days. Media coverage was intense. Headlines warned of a potential catastrophic impact, though later observations refined the orbit and showed the actual risk was zero. The Apophis case led to discussions within NASA and international space agencies about whether disclosure protocols should be revised. Should initial calculations with high uncertainty be released immediately, risking public alarm if the orbit is later refined to show no risk? Or should results be withheld until uncertainties are reduced, risking accusations of cover-up if the risk proves real? No consensus was reached. The compromise was clearer communication of uncertainty and context, but not restrictions on disclosure itself. Near-Earth object tracking in the post-2000 era operates under congressional mandate. The George E. Brown, Jr. Near-Earth Object Survey Act of 2005 directed NASA to detect and catalogue at least 90% of near-Earth objects larger than 140 meters by specific deadlines. The law includes provisions for informing Congress and international partners about detected threats. It does not authorize classification or restriction of data, except in cases where disclosure would reveal intelligence sources or methods. Under these provisions, orbital data for potentially hazardous asteroids is shared globally through the Minor Planet Center. When an object is discovered, its orbit is calculated and posted publicly within hours or days. If the orbit shows any possibility of Earth impact, the information is immediately communicated to planetary defense authorities in multiple countries through the UN-authorized International Asteroid Warning Network. The default is transparency, not secrecy. 3I, Atlas, did not fit the potentially hazardous asteroid profile. Its trajectory showed no possibility of Earth impact for at least centuries, and by the time the data restrictions were implemented, its trajectory had been refined to the point where multi-century predictions were reliable. The justification for restrictions could not be risk management in the sense of preventing premature alarm about impact. A different historical parallel involves discoveries that challenge scientific paradigms or have implications beyond their immediate field. When pulsars were discovered in 1967, the regular radio pulses initially seemed so artificial that astronomers half-jokingly labelled them LGM for little green men. The discovery was announced publicly after a few weeks, once natural explanations were explored and found wanting. Secrecy was never considered despite the potential for the discovery to be misinterpreted as evidence of extraterrestrial intelligence. More recently, the detection of phosphine in Venus's atmosphere in 2020 generated controversy not because of information control, but because of disputes about data interpretation. The initial paper reporting phosphine, a molecule associated with life on Earth, was peer-reviewed and published in Nature Astronomy. Other scientists questioned the analysis, and subsequent debate occurred openly through published papers and conferences. No one suggested classifying the data to prevent speculation about life on Venus. The controversy was resolved through normal scientific discourse. The 3I Atlas case was different. Instead of open debate about anomalous observations, the observations themselves were restricted. This prevented the normal scientific process where multiple independent groups analyze data and either confirm or refute initial findings. When data is restricted, this process cannot occur. The result is that questions remain unanswered, not because they are unanswerable, but because access to the information needed to answer them is controlled. One possible model for how 3I Atlas restrictions might have come about involves bureaucratic risk aversion. Government agencies dislike uncertainty and unfavorable media coverage. If an object is behaving unexpectedly and the implications are unclear, the safest bureaucratic response is to limit information flow until a clear narrative can be developed. This avoids the risk of releasing data that is later reinterpreted or contradicted, which would embarrass the agency and undermine public trust. But this risk-averse approach conflicts with scientific norms. Science advances through hypothesis testing, which requires proposing explanations and checking them against data. Restricting data prevents hypothesis testing. If multiple teams independently analyze the same data and reach different conclusions, that is not a problem to be avoided, but a signal that more analysis is needed. Converging on truth requires allowing diverse perspectives to engage with the evidence. The historical arc of information control in space science suggests a tension between two values. One value is transparency, the idea that scientific knowledge belongs to humanity and should be shared openly. The other value is security, the idea that some information, even scientific information, might need protection if its disclosure could cause harm. These values are not always compatible. Sometimes they require trade-offs. The question for 3I Atlas was whether the trade-offs were justified. The history suggests that unjustified restrictions do more harm than good. They damage public trust, inhibit scientific progress, and often fail to prevent the very speculations they aim to suppress. When information is withheld, people assume the worst. Conspiracy theories flourish in the absence of facts. Paradoxically, being open about uncertainty is often less damaging than being closed and creating suspicion. Threat assessment. The concept of threat assessment for celestial objects is usually straightforward. An asteroid on a trajectory that could impact Earth is assessed based on its size, composition, impact energy, and probability of collision. The Torino scale and Palermo scale quantify these factors into a single metric that communicates risk level. An object with a 1 in 10,000 chance of impact in the next century might warrant monitoring but not immediate action. An object with a 1 in 100 chance and sufficient size to cause regional devastation requires serious response planning. For 3I Atlas, conventional threat assessment frameworks did not apply cleanly. The trajectory showed no near-term collision risk. Even with non-gravitational accelerations factored in, the object was moving outward from the inner solar system and would exit beyond Jupiter's orbit within 2 years. gravitational interactions with the giant planets would further perturb its trajectory. But the calculations showed that no plausible combination of accelerations and gravitational assists would bring 3I Atlas back toward Earth on a threatening trajectory within centuries. But threat is not solely about collision. The discussions within NASA's Planetary Defense Coordination Office and in classified memos obtained by Chen considered other scenarios. What if 3I Atlas was not a natural object, even if its trajectory posed no collision risk? An object of artificial origin passing through the solar system would have profound implications. Not immediate physical threat, but strategic and existential implications about our place in the universe and the possibility of contact with other intelligences. The artificial hypothesis was not taken seriously by most scientists analyzing 3I Atlas. The isotope anomalies and spectroscopic features, while unusual, did not require artificial origin as an explanation. Natural processes in exotic stellar environments could plausibly produce the observed characteristics. The trajectory accelerations, similar to those observed for Oumuamua, could be caused by outgassing or other natural mechanisms not fully understood. Absence of definitive natural explanation does not constitute evidence for artificial origin. This is the "we don't know" category, which is common in science, not the "it must be aliens" category, which requires extraordinary evidence. But policy discussions about threat cannot entirely dismiss low probability scenarios if the consequences are significant. If there were even a 1% chance that 3I Atlas was artificial, what would that mean? The scenario analysis in classified memos explored this question not because analysts believed it likely, but because responsible planning requires considering all possibilities with non-negligible consequences. One scenario considered surveillance. If 3I Atlas were a probe from another civilization, its trajectory through the inner solar system would provide opportunities to observe Earth and other planets. The timing of its passage, while it could be coincidence, placed it in the inner solar system during a period of high human activity in space, with multiple missions to Mars, a growing constellation of satellites in Earth orbit, and renewed interest in lunar exploration. An intelligence gathering mission would find this an informative time to observe. The surveillance scenario led to questions about what information might be collected and how that might affect security. If the object were transmitting data, could signals be detected? Radio telescopes had monitored 3I Atlas for emissions and found nothing. But absence of detected signals does not prove absence of transmission. Advanced communications might use narrow beams, exotic frequencies, or encoding schemes that would not be recognizable as artificial. Or communication might occur through channels not anticipated, gravitational waves or neutrinos, or something else not monitored routinely. Another scenario considered intervention capabilities. If 3I Atlas could alter its trajectory through non-gravitational forces, did it have the capability to maneuver more dramatically? The observed accelerations were small, meters per second over hours. But what if those were the minimum necessary to maintain a desired trajectory, and larger accelerations were possible if needed? This question was unanswerable with available data, but relevant for planning. An object that could maneuver unpredictably would be difficult to track and might pose risks that stationary objects did not. The intervention scenario led to game theory-style analyses about intentions. If an intelligence chose to send a probe into another stellar system, what would its objectives be? Pure reconnaissance seems plausible, analogous to how humans send probes to explore other planets without expectation of interaction. But other objectives are possible: testing responses, demonstrating presence, or more speculative ideas involving long-term strategies that humans might not anticipate. The memos acknowledged that inferring intentions from trajectory and composition was essentially impossible. Human projections about alien motivations are likely to be wrong, but defense planning requires considering possibilities even when probabilities cannot be estimated reliably. A third category of scenarios involved unintended consequences. Suppose 3I Atlas was natural but possessed properties that could be hazardous in ways not immediately obvious. If its composition included volatile materials that could explode under certain conditions, or if fragmentation might produce numerous smaller pieces with unpredictable trajectories, the object could present risks downstream even if its current trajectory was benign. These scenarios were considered less likely than straightforward natural objects, but more likely than artificial origin. The fragmentation scenario received some attention because comet nuclei do sometimes break apart. When this happens, the fragments typically move apart slowly and remain on similar trajectories. But if fragmentation occurred explosively, perhaps due to sudden vaporization of supervolatile ices or impact by a meteoroid, the pieces could spread out with velocities that alter their trajectories significantly. A nucleus breaking into thousands of pieces would be much harder to track than a single object. If some pieces ended up on trajectories that brought them closer to Earth, managing the risk would become more complex. Risk communication was a central concern in the threat assessment discussions. How should uncertainties about 3I Atlas be communicated to the public and to policymakers? Overstatement of risk could cause unwarranted alarm and damage credibility. Understatement could leave populations unprepared if the situation evolved. Acknowledging uncertainty without clear risk estimates is difficult because both media and public often interpret uncertainty as incompetence or evasiveness. The assessment process also grappled with long-term trajectory uncertainty. While near-term predictions for 3I Atlas were precise, predictions decades or centuries into the future accumulated uncertainty. Small errors in current measurements or unknown forces affecting the object could compound over time, leading to large uncertainties in future positions. If non-gravitational forces continued, predicting where 3E8T LAS would be in 2100 or 2200 became more speculative. This long-term uncertainty meant that categorical statements about no future risk required caveats. The object would not threaten Earth soon, but what about eventually? Philosophical dimensions of threat also appeared in the discussions. If humanity's understanding of physics or cosmology needed revision because of 3I Atlas, what were the implications? Not physical threat in the conventional sense, but challenge to worldviews and frameworks that guide decision-making. Science operates on assumptions about how the universe works. When observations contradict assumptions, the challenge can be profound. This is threat to intellectual certainty rather than physical safety, but it still matters for how institutions respond. Ultimately, the threat assessment concluded that 3I Atlas posed no imminent physical danger, but represented uncertainty that warranted continued monitoring and analysis. The classification of data was justified in internal memos by reference to this uncertainty and to the potential for misinterpretation. Until the anomalies were understood, public discourse might leap to unwarranted conclusions. Better to provide clear information once analysis was complete than to feed speculation with incomplete data. But this rationale assumed that government analysis would eventually resolve the uncertainties and provide definitive explanations. What if the anomalies resisted explanation? What if the object remained mysterious even after exhaustive study? At what point does withholding information because of uncertainty become untenable? These questions were not answered in the available memos. Science versus security. The tension between scientific openness and perceived national security interests is not new, but the 3I Atlas case brought it into sharp focus. On one side stood the scientific community's foundational principle that knowledge advances through free exchange of information, peer review, and replication of results. On the other stood government agencies' responsibility to protect sensitive information that could affect national security, even when the connection between that information and actual security threats is not immediately obvious. The case for transparency rests on several arguments. First, scientific progress depends on many minds working on problems. When observations reveal something unexpected, the path to understanding usually involves multiple research teams proposing different explanations, testing them against data, and eliminating those that do not fit. This process works only if everyone has access to the same information. Restricting data to a small group of cleared analysts may protect information, but it also limits the intellectual diversity that often leads to breakthroughs. Dr. Elena Vasquez, a planetary scientist at UC Berkeley who studies cometary composition, articulated this view in an interview. She had attempted to obtain high-resolution spectra of 3I Atlas to compare with her observations of solar system comets, but encountered resistance from NASA. "Science is not done by committees working in secret," she said. "You need people arguing, proposing wild ideas, checking each other's math, finding mistakes. When you classify data, you lose that. You are left with a small group who all have similar training and perspectives. The best ideas often come from unexpected places, from someone who approaches the problem differently than everyone else." The second argument for transparency involves trust. Public trust in science and in government institutions depends on perceiving them as honest and operating in the public interest. When information is withheld, trust erodes. People assume that concealment reflects something damaging or embarrassing that authorities want to hide. Even if the actual reasons for classification are benign, the perception of cover-up damages credibility. This trust deficit makes it harder to communicate effectively about legitimate risks and to gain public support for necessary policies. The third argument concerns international cooperation. Astronomy is a global enterprise. Telescopes, spacecraft, and expertise are distributed around the world. Major discoveries often involve collaboration between institutions in different countries. When one country classifies data about an object observable by everyone, it disrupts this cooperation. Other nations may reciprocate by withholding their own observations, fragmenting the global knowledge base and slowing progress. For challenges that affect all of humanity, like asteroids that might impact Earth, or understanding cosmic phenomena that could have broad implications, international cooperation is essential. The case for security restrictions is more complex and often not articulated fully in public discussions, because doing so might reveal the very concerns that classification aims to protect. But the arguments can be reconstructed from policy documents, interviews with officials, and the logic of strategic planning. The first security argument involves preventing adversary advantage. If observations of 3I Atlas reveal something about US space tracking capabilities, sharing that information openly could help adversaries understand and potentially evade those capabilities. For example, if high-precision radar tracking demonstrates ability to detect and characterize small objects at great distances, adversaries might redesign spacecraft or debris to minimize radar signature. This is the traditional rationale for classifying intelligence-related information. It assumes that protecting sources and methods is important, even when the specific information derived from those sources is not particularly sensitive. Applied to 3I Atlas, This argument faces challenges. The existence of advanced US space tracking capabilities is not secret. The Goldstone radar system and military electro-optical tracking facilities are known publicly. Their approximate capabilities can be inferred from published specifications and from observations reported in scientific literature. Revealing that these systems tracked 3I, Atlas, with high precision adds minimal information beyond what is already public. The incremental intelligence value to adversaries seems small. The second security argument involves managing public reaction. This rationale is more about information operations than national security in the traditional sense. If data about 3I, Atlas, were released, showing highly anomalous behavior without clear explanation, media coverage could become sensationalized. Headlines might speculate about alien probes or existential threats, creating public anxiety that is difficult to manage. Even if the speculation is unfounded, the social disruption caused by widespread alarm could itself become a security issue if it undermines confidence in institutions or provokes panic-driven behavior. This argument treats information control as a tool for social stability. It assumes that elites with access to classified information can make better decisions about what the public should know than the public can make for themselves. This is a fundamentally paternalistic stance that has philosophical and practical problems. Philosophically, it conflicts with democratic principles that citizens have rights to information affecting their well-being. Practically, it often fails because attempts to control narratives in the age of social media are difficult, and leaks usually occur, often in garbled form, that causes more confusion than full disclosure would have. The third security argument concerns strategic uncertainty. When dealing with unknowns, maintaining flexibility in response options might require not committing publicly to particular interpretations or positions. If NASA announced that 3I, Atlas, was exhibiting behavior inconsistent with natural objects, that announcement would constrain future options. If the anomalies were later explained naturally, NASA would face criticism for overreacting. If the anomalies persisted and implications became more serious, early public announcements might have locked in assumptions that later proved wrong. Keeping information classified preserves option value by avoiding premature commitments. This argument has merit in fast-moving situations where understanding evolves quickly. But it assumes that the costs of secrecy are lower than the costs of transparency with uncertainty. This assumption does not always hold. Transparency with explicit acknowledgement of uncertainty can be more credible than delayed disclosure that tries to present a complete narrative. People can handle uncertainty better than they handle discovering they were kept in the dark. Who makes these decisions and how? In the US system, classification authority is vested in the executive branch, primarily in the president and in agency heads who have been delegated classification authority. For scientific data, classification decisions typically involve coordination between the agency that collected the data and relevant policy offices that assess whether national security implications exist. For 3I Atlas, the decision likely involved NASA leadership, the National Security Council, and possibly the intelligence community, if the data came from systems with intelligence functions. The process is not transparent. Classification decisions are not subject to public review. There is oversight from Congress through classified briefings to intelligence committees, but these briefings themselves are classified, so the public cannot know what Congress has been told or whether Congress endorses the classification. This lack of transparency about transparency creates a system where classification can expand without clear checks and balances. International implications of the classification created friction. Treaty obligations under the Outer Space Treaty of 1967 require nations to inform the UN and the international community about potentially hazardous objects detected in space. The treaty's intent was to prevent surprises and to ensure that potential threats to Earth were managed cooperatively rather than unilaterally. By classifying information about 3I, Atlas, the US arguably violated the spirit, if not the letter, of this treaty, though the object's lack of near-term impact risk provided a technical defense. Other nations expressed concern through diplomatic channels. The European Space Agency, which operates multiple space observatories and contributes to near-Earth object tracking, sent inquiries to NASA asking about the discrepancies between public data releases and observations made by European facilities. Russia and China, both of which have active space programs and track objects independently, noted the classification in their own internal reports and adjusted their information sharing protocols accordingly. The result was a slight cooling of international cooperation in space situational awareness, which is counterproductive given that space debris and asteroid detection benefit from global coordination. The cost of secrecy to scientific progress is measurable in delayed publications, foregone collaborations, and questions left unaddressed. Multiple research teams working on related problems were unable to publish results or had to publish partial results that omitted the most interesting findings. Graduate students whose theses depended on access to 3I, Atlas, data faced delays or had to pivot to different topics. International conferences that would normally have featured extensive discussion of interstellar objects saw limited presentations because researchers lacked data or were advised not to present certain findings publicly. The institutional cost was harder to quantify, but potentially more significant. Every instance where scientific information is classified for reasons that seem weak or pretextual reduces trust in institutions that conduct and fund science. Researchers begin to question whether their work will be supported if it produces inconvenient results. Universities reconsider whether accepting government funding is worth the risk of restrictions being imposed later. International partners become wary of collaborations that might give one nation unilateral control over data. There are contexts where science and security must coexist with some tension. Research into nuclear weapons, biological agents, or cyber vulnerabilities legitimately requires restrictions to prevent malicious use. But extending classification to astronomical observations stretches the national security justification in ways that risk normalizing secrecy in domains where openness should prevail. If comets can be classified, what else might be? Discoveries in physics that have dual-use potential? Biological findings that reveal vulnerabilities in human immune systems? The slippery slope is real and concerning. The 3I Atlas case exemplifies a system where security concerns can override scientific norms, even when the security rationale is unclear. Whether this balance is appropriate depends on values and priorities. Those who prioritize control and risk avoidance will see the classification as prudent. Those who prioritize openness and trust will see it as overreach. The debate is fundamentally about how societies should handle uncertainty about phenomena that do not fit existing frameworks. Other voices. Dr. Sarah Chen was not the only insider with concerns about 3I, Atlas, though she was the most public. Conversations with other researchers, speaking on condition of anonymity, revealed a broader pattern of unease within the planetary science community. Many had observed anomalies or encountered obstacles accessing data, but few were willing to risk their careers by speaking publicly. One researcher at the Jet Propulsion Laboratory, who declined to be identified even anonymously beyond general institutional affiliation, described internal meetings where 3I, Atlas, was discussed. The official line was always that the object was under study and results would be released when analysis was complete, they said. But in private conversations, people were more candid. The isotope data did not make sense. The trajectory deviations were larger and more irregular than models predicted. There was genuine puzzlement about what we were looking at, but also clear guidance from management not to speculate publicly. This researcher noted that the classification created a two-track conversation. In classified briefings, analysts could discuss the full range of hypotheses, including exotic ones. In public forums, and even in unclassified internal meetings, only sanitized discussions were permitted. It was frustrating, they said. You had this interesting scientific problem, exactly the kind of thing that gets people excited, and we couldn't talk about it openly. Young researchers wanted to work on it, but were told their results might be classified, which complicated publication and career advancement. So they chose other projects. A European astronomer at the Max Planck Institute for Solar System Research had a different perspective from outside the US system. They had observed 3 IATLAS using the Very Large Telescope in Chile and had noted some of the spectroscopic features that US researchers found unusual. We published preliminary results in an IAU telegram, they said, referring to the International Astronomical Union's rapid communication system for astronomical discoveries. The features were there. We did not know what to make of them, so we just reported the observations and said they were interesting. No drama, no speculation. What struck this researcher was the contrast in how European and American institutions handled the findings. In Europe, unusual observations get published and the community discusses them. Consensus builds or does not build based on evidence. In the US, for 3I, Atlas, there seemed to be gatekeeping. Data was released selectively. Papers encountered unusual delays. It felt like someone was trying to control the narrative rather than letting science proceed normally. International observers also noted discrepancies between data they collected independently and what appeared in official databases. China's Purple Mountain Observatory, which tracks asteroids and comets systematically, found that their measurements of 3I Atlas's position sometimes diverged from NASA's published orbital elements by more than expected from measurement uncertainty. The divergences were small, only hundreds of kilometers, but they were consistent and suggested that the public orbital elements had been smoothed or averaged in ways that obscured short-term variations. When Chinese astronomers contacted the Minor Planet Center about the discrepancies, they received explanations citing differences in observation, timing, and data processing methods. These explanations were plausible but did not fully account for the pattern of divergences. The Chinese team published their observations in a domestic journal but did not push the issue further publicly. Privately, some Chinese researchers suspected that the public data was being sanitized to hide something, but without access to classified US information, they could not confirm this suspicion. Public statements from NASA and affiliated researchers were carefully crafted to provide information without revealing classified details. Dr. Lindley Johnson, then leading NASA's Planetary Defense Coordination Office, gave several interviews about 3I Atlas, in which he described the object as scientifically interesting and providing valuable data about interstellar comets. When asked about reports of trajectory, anomalies, he acknowledged that all comets exhibit non-gravitational forces due to outgassing, and stated that such forces were within normal ranges for comets of this size. These statements were technically accurate, but omitted the context that the pattern and magnitude of 3I, Atlas's accelerations, were unusual compared to well-studied comets. The absence of denial is sometimes as informative as explicit statements. When Science magazine published an article in May 2025 discussing the insider revelations and the classification controversy, NASA issued a brief response stating that the agency takes its responsibilities for national security and scientific integrity seriously, and that all decisions regarding data management are made in accordance with applicable laws and regulations. The statement did not deny that data had been classified. It did not refute specific claims about trajectory anomalies or compositional oddities. It simply affirmed that proper procedures had been followed. Legal scholars who analyzed the statement noted that it was consistent with an organization that had classified information and was constrained in what it could say publicly. If the revelations were inaccurate, NASA would likely have said so explicitly. The lack of specific refutation suggested that the core claims were substantially correct, even if NASA disagreed with characterizations or interpretations. Other government agencies were even more reticent. The National Reconnaissance Office, which operates classified surveillance satellites and would likely have observations of 3I, Atlas, from those assets, declined all requests for comment. The Department of Defense, whose tracking systems monitor space for potential threats, issued a statement saying that all information related to space domain awareness was subject to classification review and that no details could be provided about specific objects. These non-responses confirmed that other agencies were involved, but provided no insight into what they knew or assessed. Congressional oversight of the situation was limited and mostly classified. Representative Mark Pocan of Wisconsin, a member of the House Appropriations Subcommittee on Commerce, Justice, and Science, asked NASA administrators about 3I Atlas during a budget hearing in June 2025. The exchange was brief and uninformative. Pocan asked whether there were any concerns about the object that should be shared with Congress or the public. The NASA administrator responded that the object was being monitored closely and that appropriate briefings were provided to relevant committees. Pocan followed up, asking whether classification of scientific data was appropriate for an object posing no near-term threat. The administrator answered that classification decisions are made by interagency process and NASA defers to national security expertise on such matters. This exchange illustrated how congressional oversight often fails to penetrate executive branch secrecy. Even members of Congress, who have constitutional responsibility for overseeing the executive, found it difficult to get straight answers about classified programs. Classified briefings to congressional committees occurred, but were themselves secret, so the public could not know whether Congress was satisfied with the explanations or shared concerns about overclassification. The pattern of silence among those who know suggests that information is being controlled effectively. When multiple independent sources all decline to comment or provide only carefully scripted statements, it indicates coordination and enforcement of communication discipline. This is what intelligence and security agencies excel at, managing information flows to prevent leaks and unauthorized disclosures. For 3I, Atlas, the coordination appeared effective. Despite the initial revelations from Chen, no flood of additional whistleblowers emerged. Either few people knew the full picture, or those who did know were successfully deterred from speaking. The deterrent effect of classification is powerful. Legal penalties for unauthorized disclosure of classified information include fines and imprisonment. Security clearances, which are required for many government and defense contractor positions, can be revoked for violations. Professional reputations can be destroyed. The risks are substantial, and most people with access to classified information take those risks seriously. Whistleblower protections exist, but are limited, especially when national security classifications are invoked. The calculus for someone considering disclosure is daunting. Public interest organizations advocated for transparency. The Federation of American Scientists, which has long worked to reduce excessive government secrecy, issued a statement calling for declassification of 3I Atlas data unless specific national security harms could be demonstrated. The Planetary Society, a non-profit space advocacy organization, published an editorial arguing that scientific discoveries about interstellar objects belong to humanity and should not be restricted without compelling justification. These organizations had no power to compel disclosure, but could influence public opinion and congressional willingness to demand answers. Media coverage of the 3I Atlas controversy was extensive but varied in quality. Some outlets reported the story responsibly, presenting what was known, what was alleged, and what remained uncertain. Others sensationalized, running headlines about government cover-ups and alien probes without evidence supporting such claims. The sensationalism ironically validated NASA's concerns about public misinterpretation, though it also resulted partly from the vacuum of official information. If NASA had been more forthcoming about uncertainties and anomalies, responsible journalism could have filled the information space and crowded out speculation. The scientific community's response was divided. Some researchers supported Chen's decision to disclose, arguing that transparency was essential. Others criticized the disclosure as irresponsible, arguing that classified information should stay classified regardless of personal opinions about its justification. This division reflected broader debates in science about the relationship between researchers and government, about whether scientists have obligations that transcend institutional loyalties, and about when disclosure serves the public interest. What remains clear is that many knowledgeable people, inside and outside government, saw something about 3I Atlas that troubled them. Whether their concerns were justified by objective analysis or reflected over-interpretation of ambiguous data is a question that cannot be definitively answered without access to the full classified record. But the pattern of concern, expressed independently by multiple sources, suggests that whatever was observed did not fit comfortably into existing frameworks. When faced with such anomalies, the response says much about institutional values and priorities. Transparency and trust. The 3I Atlas episode reveals fundamental tensions in how democratic societies handle scientific information with potential security or social implications. These tensions are not new, but the specific circumstances of an interstellar object exhibiting anomalous behavior bring them into focus with unusual clarity. The questions raised extend beyond this single case to the broader relationship between science, government, and the public. The case for transparency rests on principles that are foundational to both science and democracy. Science advances through open exchange of information. Hypotheses are tested against evidence that anyone can examine. Mistakes are caught through peer review. The best explanations emerge from competition among ideas, not from authority determining what is correct. When observations are classified, this process breaks down. A small group decides what is true and what the public should know. This is antithetical to scientific method. Democracy similarly requires informed citizenry. People cannot make good decisions about policies and priorities if they lack access to relevant information. When government withholds information, even with benign intent, it treats citizens as subjects rather than participants in governance. Trust erodes when people discover they were kept in the dark, especially if the reasons for secrecy seem weak in retrospect. The history of government overclassification is long, and declassified documents frequently reveal that much of what was secret had no legitimate need for classification. The frustration in the scientific community about 3I Atlas reflects these principles. Researchers are trained to question, to probe, to demand evidence. When authority says, "Trust us," we cannot tell you why, but classification is necessary. Scientists instinctively resist. This resistance is healthy. It is the attitude that drives discovery and prevents errors from becoming entrenched. Suppressing it in the name of security carries costs that may exceed the benefits of control. But the case is not simple. National security is real. Information can cause harm. The question is not whether any classification is justified, but whether classification of 3I, Atlas data, specifically was justified. Reasonable people can disagree on this, and the disagreement reflects different weightings of competing values. Those who defend the classification argue that when uncertainties are large and implications potentially significant, caution is appropriate. If 3I, Atlas's anomalies, suggested even remote possibilities of exotic origins or unexpected physics, managing how that information reached the public could prevent misunderstandings with serious social consequences. Public panic, international tensions, or political crises driven by misinterpreted data would serve no one's interests. Better to understand the situation fully before disclosure, even if that means delay and restricted access. This argument assumes that authorities can be trusted to eventually disclose once understanding is sufficient. It assumes that the decision makers are acting in good faith and that their judgment about when disclosure is appropriate will be reasonable. History provides mixed support for these assumptions. Governments do sometimes declassify information when the rationale for secrecy ends, but they also maintain unnecessary classifications for decades, protecting bureaucratic interests more than security. The long-term consequences of information control include erosion of public trust in institutions. Each instance where secrecy seems excessive or where disclosed information reveals that earlier official statements were incomplete reinforces cynicism about government. This trust deficit makes future communication harder. When NASA says an asteroid is not a threat, will people believe it if they remember times NASA withheld information? When a genuine emergency requires public cooperation, will people follow guidance from agencies they distrust? The scientific community's frustration is compounded by knowing that progress is being slowed. Multiple researchers working independently on 3I Atlas could have resolved the anomalies faster than a small classified group. Diverse perspectives and expertise, unrestricted data access, and open discourse accelerate discovery. By restricting information, the classification ensured that whatever 3I Atlas represents would take longer to understand than if science operated normally. International tensions created by the classification will have lasting effects on cooperation. The space domain increasingly requires international coordination. Asteroid detection, space debris tracking, planetary defense, and scientific missions all benefit from nations sharing data and working together. When the US classifies information about an object visible to all, it signals a preference for control over collaboration. Other nations will remember this when deciding whether to share their own data in future situations. The result could be fragmentation of the global space situational awareness network, making everyone less safe. What should have happened differently? Multiple paths existed that might have balanced transparency with legitimate concerns. One option was qualified disclosure, releasing the data along with explicit caveats about uncertainties and competing interpretations. This approach treats the public as capable of handling complexity. It provides information while being clear about what is known versus what is speculated. Media coverage might still sensationalize, but reporters and public would have access to accurate data rather than rumors and leaks. Another option was time-limited classification with automatic declassification after a specified period, say 6 months. This would allow initial assessment without permanent information control. It would signal that secrecy was temporary and driven by legitimate need for analysis time rather than desire for indefinite control. When the time limit expired, all data would become public, regardless of whether all questions had been answered. This forces agencies to focus on the most essential security concerns and accept that some uncertainty will remain even at disclosure. A third option was international collaboration from the start. Instead of unilateral US classification, NASA could have coordinated with ESA, JAXA, and other major space agencies to develop a joint assessment. This distributed responsibility for managing information while ensuring that no single nation could dictate terms. It would have been messier and required compromise, but would have preserved international trust and leveraged global expertise. The path actually taken, unilateral classification with selective disclosure, was perhaps the worst option. It generated suspicion without providing security benefits commensurate with the costs. It slowed scientific progress without preventing speculation. It damaged trust without protecting genuinely sensitive information. These outcomes were predictable and should have informed decision-making. The broader implication is that institutions need better frameworks for handling scientific information with possible security or social dimensions. The current system, where classification authority is broad and oversight limited, allows excessive secrecy. Reforms might include requiring explicit evidence of specific harms that disclosure would cause, mandatory declassification reviews on fixed schedules, and enhanced congressional oversight with authority to challenge classification decisions. These reforms would not eliminate legitimate classification, but would make unjustified secrecy harder to maintain. For 3I, Atlas specifically, the situation remains fluid. The object is moving outward from the inner solar system and will eventually become too faint to observe without enormous telescopes. Some questions may remain forever unanswered if observations needed to resolve them cannot be made before the comet becomes undetectable. This would be unfortunate but not catastrophic. Science often lives with unanswered questions, and some mysteries persist for generations before yielding to new observations or theories. What matters more than resolving the specific mysteries of 3I, Atlas, is learning institutional lessons about transparency. The episode demonstrated that classification can be applied to scientific observations without clear justification. It showed that bureaucratic risk aversion and desire to control narratives can override principles of openness. It revealed that current oversight mechanisms are insufficient to prevent overclassification. These are not problems specific to this case, but systemic issues that affect how societies handle many types of information. The insider who came forward, Dr. Sarah Chen, took enormous personal risk to bring these issues to light. Her career consequences were severe. She lost her security clearance and her position at NASA. Job offers from academic institutions were complicated by concerns about her access to sensitive material and potential legal liabilities. Yet, she expressed no regret. In a rare public statement, months after her disclosure, she wrote, "Science is a public good. When institutions try to privatize knowledge or control access to information that belongs to everyone, someone must object. I had the access and the expertise to know what was happening. I had a responsibility to act." This sentiment resonates beyond 3I, Atlas. In an era of increasing government secrecy, technological surveillance, and information control, individuals with access to truth face choices about whether to speak. Whistleblower protections are limited, and retaliation is common. Yet disclosure serves an essential function in maintaining accountability and preventing abuse of power. Without people willing to take risks to expose unjustified secrecy, the scope of classification would expand without limit. The 3I Atlas case will be studied in courses on science policy, information security, and government transparency. It will appear in discussions of how societies balance competing values and how institutions respond to uncertainty. Future policy decisions about classification of scientific data will be influenced by this episode and by how the debate evolves. Whether the influence is toward greater openness or greater control depends on which lessons are emphasized and which constituencies prevail in shaping policy. For now, the tension remains unresolved. 3I Atlas is gone, moving beyond the range of detailed observation, carrying its secrets into the darkness of interstellar space. The questions it raised about information control, scientific freedom, and institutional accountability remain. These questions matter not because of one comet, but because they reflect fundamental challenges in governing complex technological societies where knowledge is power and those who control knowledge shape reality for everyone else. How we handle these challenges will determine whether scientific progress serves all humanity or only those with access to the full picture.